Hello everyone and welcome to the NumPy Jupyter Notebook intro. Here we'll go over the basic operations in NumPy and hopefully you'll have a better understanding of some of them and then you can move on to exploring other resources. Cool. So let's start. What is NumPy? It's a library in Python that is useful with n-dimensional array objects, sophisticated functions, great for integration with other code and languages, and it's useful in linear algebra and other mathematical functions. This image right here is a great image if you are interested in learning about the granular differences between a NumPy array and a regular array, and why it's more advantageous to use NumPy in math instead of a regular array. But we're not going to go over that at this moment, but feel free to explore that if you are interested. So we start by importing NumPy. This is the version that we have. So let's start with creating a NumPy array. In this first cell, you can see that we have list 1, 1, 2, 3, 4, and we're converting it to a NumPy array. And now we want to see what that looks like. So here, it's a NumPy array with the contents 1, 2, 3, 4. What data type would it be? It's going to be a NumPy array. What data type will be stored in the array, and those are going to be integers. Here, what are we doing? We want to put a float into the 0th index. So remember, these are all 0 indexed arrays. So the first element technically has a 0 index. So the first element is being casted to 3.14159, but because these are integers and not floats, it's going to be upcasted to an int right here. So we only see 3 in the beginning. Now we can continue by looking at what is happening here. There's a data 2 NumPy array. We're printing that, and then we want to print the type. So these next few cells are basically deal with looking at different data types and how that works. Some of the errors we might see, some discrepancies. All right, so let's move on to slicing and indexing. Right here, so we have a NumPy array with range 10, which means it'll be from 0 to 9. We want to print, oh, okay, I see. So we're slicing it here, right? So for slicing, you use the colon. The number right before the colon is inclusive, and the number at the end of the colon is exclusive. And it deals with the indices that the array has. So the first one has no values passed in the beginning or after. So it's the entire NumPy, the entire array, which is 0 to 9. The next one is 0 to 3, which means we have indices 0, 1, 2, which is right here, 0, 1, 2. And here it's the third index and after, which is 3 to 9, right? If you put a -2, so if you do this, you're basically, this is step. If you have 2 colons and then the argument after that is step, and because it's a negative number, you're basically stepping by 2 backwards, which is 9, 7, 5, 3, 1. And then again, this is another example of slicing. A lot of these examples and documentation for this can be found on numpy.org, or just searching up documentation. I find myself, again, even forgetting some of these little rules. But if you do search it up, it's very easy to find. So arrays are like lists, but different. NumPy utilizes efficient pointers to a location in memory, and it'll store the full array. On the other hand, lists are pointers to many different objects in memory. So what's happening here, right? We store a NumPy array in data. View is 0 to 3, and we want to print that. So here we have, so we're using slicing, and we're getting the 0th first and second index because 3 is exclusive. Here, if we continue, we're copying the list, which is L, right? And we're printing it because we're assigning this 0 to 3 to copy, and then we're just printing that, which is the same thing as above. Here, we're setting the 0th index of copy to 99, the 0th index of view to 99, and we want to compare them, which is the same thing because up here we see view and copy are essentially the same. And that's why right here, they're also the same. So now we want to print the Python list and the NumPy array. If you see, the Python list originally has not changed, but the NumPy array has, right? Because if you print L, that's right here. You were changing the copy with by printing this and by changing this 99, but you weren't changing the original list itself because it's a copy of it and not a pointer. So here we're creating copies of the array instead of views. And now when we do this, it's no longer a view. And then when we have X's NumPy array of range 20, you're printing that, and now you want to assign it to Y. So this is basically 0 to 19, right? Because range 20 returns 0 to 20, but exclusive of 20, which is 19. It would be the max. So now you're slicing Y from beginning to end with 0. And see, now we print all zeros because you're replacing every single element with 0 now. See, so if X was a copy of Y, this would return false. But X and Y are in fact the same exact array. And that's why this is happening here. Here, however, just because X and Y are the same exact arrays, or sorry, are equal arrays, doesn't mean that X is Y, because they're both they're very independent. If you change X here, then nothing will happen to Y. If you change Y here, nothing will happen to X. So now we want to work on making training and test sets, right? A lot of the things that we can do with training and test sets revolve around using shuffle and random shuffle. You can explore this further by looking at some documentation. So why use arrays over lists? Mainly because arrays are just a lot faster than lists. Here, we have a list of this range, and here we want to square all elements, right? So you can, I'm running this, and this is basically telling us why lists are slower than arrays. So the time for Python lists, this is how long it took, which is longer than it would take an array, because an array stores it in memory, and a list requires you to iterate through the entire thing to do those operations. So now look at how much the difference in time that it took between the list and arrays. This is significantly faster. I'm going to be honest, I don't know what this is called, this unit, but it is a lot faster than this millisecond. So look, NumPy is 648 times faster than lists at squaring 100,000 elements. Let's move on to universal functions. So basically, just backtracking a little bit, this just shows why people prefer to use NumPy when the same operation can be done with lists. It's mainly because the time it takes is significantly slower. So when you have huge data sets and enormous operations, then having something that can be almost 650 times faster is very, very useful. Move on to universal functions. We have list X and list Y. We're just declaring them here and we're printing them. And then here we're adding them, right? Which doesn't add the elements itself, it adds the two lists together. So it's going 0, 1, 2, 3, 4, and it's basically putting this list Y behind the list X. But now with arrays, because they're mathematical, what's happening now? We're actually adding the elements themselves. See, so the 0th indexes are being added, the first indices are being added, so the second indices are being added, and so on. So this is how, again, this is how we're keep making sure that it still stays an NumPy array by doing this, because then see right here we have NumPy array of the addition, and here is just a regular array. So just more operations using both of them. So now for more mathematical operations with arrays and lists. So we're printing the two, if you need to join NumPy arrays, right? Because earlier when we did the plus, it joined the two lists, but it would add the two arrays. So how do we join the arrays? This is how you do it. You do np.hstack. Again, and these are all different alternatives that you could use to add them. It just you can choose whichever you prefer. And you can find these very easily if you start exploring how to look at NumPy documentation. So these are just other examples. VStack actually puts them in two different indices instead of adding them into one array. And then column stack stacks them into columns. So then the 0th indices are right here. The first indices are right here. The second indices are right here. So just different types of combining them depending on whatever your use case is. And here is the same thing as hstack. We're just putting it all into one array. So now we're looking into multi-dimensional arrays, right? How are we doing that? This list has two different dimensions. And then we're having an array right here that also has two dimensions. So attributes of a multi-dimensional array. How many dimensions does it have? 2. What's the shape? It's 2 by 3. This is the size of it. This is finding the transpose. Yeah, so this is just different linear algebra functions you can do and how to do them. So this Jupyter Notebook goes to continue to other ways to create NumPy arrays. They give you multiple different options for what you want and how you want to do it. It's great that it has so much flexibility. Feel free to run through these cells yourself, just giving you some useful indexing strategies. But just know that a lot of this stuff can be found on the internet. But it's great to know how to do each operation at least one way. But if you do find yourself wanting to use a different way, that should not be too bad. Yeah, so this is masking it and more NumPy array methods. You can do reshape, ravel, cumulative sum. So yeah, so the rest of this notebook is basically just additional things you may find useful in NumPy. There are tons of mathematical operations you can do. Basically anything you can do on paper, you can do in NumPy with math. So there's an example of prediction, right? It's great for probability. And now we have, at the end, there are some exercises for you to be able to do yourself to get to learn it as great as possible. Yeah, I hope this was very helpful this notebook is helpful in helping you get a good introduction to NumPy. If you are looking for more resources, feel free to navigate to our external links and additional references. There's great examples on YouTube